Good morning, everyone. I am Michele Pierallini, and the title of my work is Swing Up of Underactuated Compliant Arms via Iterative Learning Control. The goal of this work is to swing up an underactuated compliant arm via Iterative Learning Control. In particular, we present the following contribution. We design an iterative learning controller which combines feedback and feed-forward terms. We prove the iterative learning control law convergence. We track the desired trajectory. We stabilize the system in the vertical position while preserving its elastic behavior. And finally, we validate the effectiveness of the method via simulations and experiments. This is the model of the compliant underactuated arm, and it's worth noting that S is the underactuation matrix. Now we present a condition to preserve the elasticity of the robot. So if the feedback controller is bounded, then the distance between the open and closed loop stiffness is bounded too. This means that the elasticity of the robot is not drastically altered. This is the iterative learning control law, which combines feed-forward and feedback terms. Additionally, the tracking error is defined as, and it's worth noting that the iterative learning controller is based on the output feedback. Now we present sufficient conditions to guarantee the convergence of the iterative method. In particular, if the learning gains are such that, then the iterative controller approaches the desired controller with a bounded error. Now we present a procedure to select the learning gains of the iterative method. In particular, if we set learning gains equal to this, we obtain the stability of the equilibrium point, the preservation of the elastic behavior of the robot with a factor beta, and finally the convergence of the iterative method. Now we start validating the effectiveness of the iterative method, and we start simulating the dynamics of a 3 degrees of freedom robot. In particular, the first elastic joint is actuated and the other two are passive with stiffness equal to 1. Then we perform a minimum trajectory with final time equal to 5 seconds, and we choose as an output function the angular position of the tip of the robot, which leads to this decoupling matrix. For the experimental validation of the method, we use a 2 degrees of freedom robot, where the first thick elastic joint is actuated and the second is passive. We perform a minimum trajectory varying its final time, and in particular we vary the velocity of the trajectory itself. Additionally, we vary both the stiffness profile of the robot and the payload of the robot. We choose as output function the angular position of the tip of the robot, which leads to a decoupling matrix equal to this. Here we report the result of the experimental validation in the case of payload equal to 0.25 kilos and in the stiffer profile, so the preset is equal to 20 degrees. And finally, here we report the experimental results in the case of payload equal to 0.35 kilos and with soft stiffness profile, which is equal to 16 degrees. Thank you for your attention.